In today's lecture on BME 417, we shall discuss feedback and its role in control systems. Here are some of the lesson objectives. The objectives of the lesson are to explain the concept of feedback in control systems, identify and explain the differences between positive and negative feedback mechanisms, including their effects on system behavior. Describe how feedback helps to compare actual output with the desired output. Analyze the mathematical representation of positive and negative feedbacks, and evaluate the stability of feedback systems. What is feedback? Feedback in control systems actually refers to the process of returning part of the output signal to the input. When a control system is able to return the output or part of the output signal back to the input, we say there is feedback. Usually, the return signal is used to adjust the behavior of the system, ensuring that it meets the desired objectives or compensate for disturbances. So usually the purpose of feedback is to be able to bridge the gap between the actual output and the desired output. If the actual output is not close to the desired output, normally there is feedback to return the output, some part of the output back into the input so that the desired output can be achieved. Here are some of the roles of feedback. They include error reduction. As I just mentioned, feedback compares the actual output to the desired output and reduces error signals. Secondly, it ensures that there is stability, especially for negative feedback. Negative feedback helps to minimize errors and also lead to stability of the system by counteracting the changes that could lead to oscillations. So negative feedback helps to create stability of the system. Then the third benefit of feedback is that feedback influences the dynamic response of the system. It influences the dynamic response of the system, allowing control over certain characteristics like speed, rise in time, and damping. So with feedback, those features can be adjusted. Also, feedback helps the system compensate for external disturbances. When there are external disturbances, feedback can help the system to compensate for it, maintaining consistent output performance. Then also, feedback can adjust the gain of the system, either increasing the gain or decreasing the sensitivity of the output. Feedback can do that relative to the input, thus modifying overall system behavior. So feedback can, to a large extent, influence the gain of the system. Let's look at types of feedback. The two major types of feedback are positive feedback and negative feedback. Positive feedback and negative feedback. Positive feedback is a type of feedback mechanism in which a portion of the output signal is fed back to the input in such a way that it is added to the original input signal. So in positive feedback, when some part of the output is fed back to the input, it is added to the original input signal, thus amplifying the signal. So in positive feedback, there is a reinforcement or amplification of the input, making it larger and leading to a cumulative effect. Here is the diagram for positive feedback system. You can see the G, which is the open loop gain. You can have also the arrow from the output going to the input. This is the feedback gain, and this is the comparator. This is the reference. So in positive feedback, you can see the positive and positive values are the comparator. Let's look at the mathematical representation of positive feedback. In a system with positive feedback, the output y of s in terms of input x of s and the feedback gain h of s is given by y of s, which is the output, is equal to g of s over 1 minus g of s h of s times x of s. So where g of s is the forward transfer function, h of s is the feedback transfer function, and we realize when you look at the denominator 1 minus g of s h of s, it to a large extent determines the stability of the system. So if g of s h of s is greater than or equal to 1, the denominator approaches 0, leading to instability or oscillations. So that is what happens in positive feedback. As much as possible, g of s times h of s should not be equal to 1 or greater than 1. Once that happens, it leads to instability of the system because 1 minus 1 is equal to 0. And once the denominator in a fraction is 0, it means that the output is infinity, which makes the system unstable. The features of positive feedback. 1. Signal amplification. Positive feedback increases the magnitude of the input signal by adding a part of the output back to the input. That is one advantage of positive feedback. Also, cumulative effect. Each cycle of feedback builds upon the previous one, amplifying the overall output progressively. That is another feature of positive feedback. Thirdly, it could lead to potential instability. So if the gain of the system g of s times h of s is greater than or equal to 1, the system can become unstable, leading to uncontrolled oscillations. Let's look at some solved examples on open loop control system. Example 1. A system with an open loop gain A of 50 has a feedback factor beta is equal to 0.02. Calculate the closed loop gain AF with positive feedback. The formula for the closed loop gain with positive feedback is given by AF is equal to A over 1 minus A beta, given that A is equal to 50 and beta is equal to 0.02. So you can see that the feedback factor beta is equal to 0.02. So when we substitute them into that equation, we have AF is equal to 50 over 1 minus 50 times 0.2. So 50 times 0.02, not 0.2, gives you 1. 1 minus 1 is equal to 0. So once the denominator is 0, the system becomes unstable. So this results in a division by 0, indicating the system reaches instability or oscillations. So positive feedback under these circumstances lead to sustained or increasing oscillations. Another example, example 2. A feedback system has an open loop gain A is equal to 100 and a feedback factor beta is equal to 0.01. Verify if the system will oscillate. Oscillation condition. For oscillation, A times beta is equal to 1. So now let's substitute the values. A there is 100 and beta is equal to 0.01. So A times beta is equal to 100 times 0.01 is equal to 1. So since A times beta is equal to 1, the system satisfies the condition for oscillation. Because when we go back to the equation, we find out that the denominator will be 0. 1 minus A times beta will give you 0. And once the denominator of an equation is 0, it means that the output will be infinity, leading to instability or oscillations. Applications of positive feedback. Positive feedback is deliberately used in special systems where amplification or oscillation is desired. So here are some of the applications. Positive feedback is used in electronic oscillators, for example, in sine wave or square wave or pulse generators. In such situations, we can use positive feedback to maintain continuous oscillations without an external input signal. So also in digital electronics, positive feedback is employed in circuits like flip-flop to maintain stable states of 0 or 1 for memory and logic operations. In radio receivers, positive feedback can increase sensitivity and selectivity, enabling weak signal amplification. Because we know that positive feedback can lead to amplification of signals. Also, some physiological processes use positive feedback for rapid response. For example, during childbirth, the oxytocin hormone is released to amplify uterine contractions. So sometimes when women want to give birth to their child, sometimes their oxytocin hormone they are injected with oxytocin hormone to increase their level of contraction during this delivery. So that is positive feedback. Now let's look at negative feedback. Negative feedback is a control mechanism in which a portion of the output is fed back to the input in such a way that it reduces or counteracts the input signal. So you can see the difference between positive and negative feedback. Why in positive feedback, yes, a portion of the output is fed back to the input, but the purpose in positive feedback is to boost the output rather than reducing the output. But in negative feedback, when we feed back a portion of the output, the purpose is to reduce or counteract the input signal. So in negative feedback, it's widely used in control system for the sake of system stability, to stabilize, regulate, and improve the performance of the system by minimizing deviations from the desired outputs. Here is the diagram for negative feedback. You can see the open loop gain, the feedback gain. You can see the outputs there, and you can see the reference. So you can note the sign, the change in sign in negative feedback. At the top we have positive sign, the plus sign. Bottom you have negative sign. While in positive feedback, both of them are plus plus. But in negative feedback, it is plus minus. So let's look at the mathematical representation of negative feedback. For a system with negative feedback, the output y of s in terms of input x of s, forward gain g of s, and feedback gain h of s is given by y of s is equal to g of s over 1 plus g of s h of s, where g of s is equal to the forward transfer function, h of s is the feedback transfer function, and we have 1 plus g of s h of s, which is the feedback loop gain. So here we can see that the denominator, the equation in the denominator is a positive sign instead of a negative sign that we have in positive feedback. So for the negative feedback, the denominator here is 1 plus g of s h of s. So this ensures that the system responds appropriately to disturbances, improving stability and reducing errors, because you can see that now we can only add 1 to the feedback control loop. So there will not be any chance of it getting to infinity, getting to 0, or getting the denominator to be equal to 0. And once that happens, the system with stability will increase because the denominator cannot be 0 and there will not be infinity at the end of the day as output. The features of negative feedback. Negative feedback minimizes the difference between the actual output and the desired output, reducing system error and enabling accuracy. That is one of the benefits of negative feedback. Also, as I said earlier, negative feedback helps the system to be stable. By opposing changes, negative feedback stabilizes the system, preventing unwanted oscillations and improving overall reliability. Also, negative feedback enhances precision in control systems by reducing the effects of external disturbances and internal variations. Negative feedback helps in noise reduction. It suppresses noise in the system by countering the unwanted components in the output signal. Negative feedback also controls the gain by reducing the effective gain of the system, making the system less sensitive to variations in component parameters. Here is a solved example. An amplifier has an open loop gain A of 1000. A negative feedback network is added with a feedback factor beta of 0.01. Calculate the closed loop gain AF. Let's look at the solution. The closed loop gain for a system with negative feedback is given by AF is equal to A divided by 1 plus A beta. So when we substitute the value, we know that the open loop gain A is 1000. Then over 1 plus, that was in 1000 times the feedback factor 0.01. So when we substitute it, we have 1000 over 11, approximately 90.91. So the closed loop gain of the amplifier is approximately 90.91. Let's look at another example. A control system has a desired output of 100 units. Due to an open loop gain configuration, the output varies by plus 20%. When negative feedback is applied with a feedback factor of 0.2, calculate the system's new steady-state output. The solution: the steady-state output in a feedback system is given by y is equal to r plus a beta. So where R is equal to 100, which is the desired output, A is equal to 1.2, which is the open loop gain, and beta is equal to 0.2, which is the feedback factor. When we substitute it into that equation, we have y is equal to 100 divided by 1 plus 1.2 times 0.2, which gives us 80.65. The steady state output is approximately 80.65. Let's look at the third example. A system has an open loop transfer function g of s is equal to 10 divided by s into s plus 2. A feedback transfer function h of s is equal to 1 is added. Determine the closed loop transfer function. Let's look at the solution. The closed loop transfer function T of S is given by T of S is equal to G of S divided by 1 plus G of S H of S. So now let's substitute G of S is equal to 10 over S plus 2 as given in the equation. We are told in the equation that the open loop transfer function G of S is equal to 10 over S into S plus 2. So wherever we see G of S, we replace it with what? 10 divided by S into S plus 2. So let's come back to this equation. T of S is equal to G of S, which is what? 10 over S into S plus 2, divided by 1 plus G of S, which is also 10 over S into S plus 2, times H of S. And H of S is what? 1. So once we do that, we have this equation, T of S is equal to 10 over S into S plus 2 plus 1 plus 10 into S divided by S into S plus 2. When it is solved, we have T of S is equal to 10 over S squared plus 2S plus 10. This form shows that the system stability is enhanced by feedback. Let's look at the fourth example. An amplifier produces a distortion level of 10% at an open loop gain of 1000. If negative feedback reduces the gain to 50, calculate the new distortion level. The distortion D is inversely proportional to the closed loop gain. Therefore, we use this formula. DF is equal to DO times A over AF. Now, let's substitute the formula. We have A is equal to 1000. That is the open loop gain. They have A, the gain, the feedback gain as 50. So when we substitute it, we have 0.1 times 1000 divided by 50. We get the final value at 0.02 or 2%. In conclusion, feedback is a fundamental concept in control systems. It plays a critical role in ensuring the desired performance of a system by returning a portion of the output signal to the input to regulate and refine the system's behavior. Negative feedback helps to stabilize systems, reduce errors, improve accuracy, and enhance noise rejection, making it essential for maintaining system stability. While positive feedback amplifies the input and achieves specific desired effects. And this is all. The application of positive feedback is well seen in oscillations and can make the systems to oscillate. The principles of feedback can enable engineers to design systems that are robust, efficient, and adaptable. Thank you for listening.